Today's lesson is a continuation from the normal distribution and empirical rule lesson. So if you have not watched the lesson on normal distribution and the empirical rule, you should check that out first before watching this one. Today, I want to talk about z-scores. Like it says here on the screen, a z-score is a measure of how many standard deviations some value is above or below the mean. Meaning, it is measuring the same type of stuff. It's still a measurement of standard deviation. The idea is, when we talked about the empirical rule, we did the 68%, the 95%, the 99.7%, but those were only specifically for the first, second, and third standard deviations, respectively. What happens if we have a data value that doesn't happen to perfectly line up on the first, second, or third standard deviation? Meaning we have some decimal in between 1, 2, and 3. In that scenario, we would want to use a z-score. As you can see here, the way you find a z-score is you take the data value, meaning whatever value you have been given for that specific question, that specific problem, take that minus the mean, and divide it by your standard deviation. And that will give you a number that will represent how many standard deviations that value is from the mean. Consider this example. Sarah and Alicia are comparing scores on their college entrance exams, meaning the SAT and the ACT. Sarah's SAT score is 1380. Alicia's ACT score is 32. The mean score for the SAT that year, at least, is 1,000, with a standard deviation of 200. And then we are also told that the mean score for the ACT is 21, with a standard deviation of 5. And it wants us to decide who actually scored better comparatively. Now, we have been given enough information here. We could just draw out a normal distribution curve for each of these, and then, estimate by looking at their standard deviations. But if we want to know exactly how many standard deviations each of them is from the mean, the best way to do that would be to calculate a z-score. So let's calculate Sarah's z-score first. Remember, like we just talked about, the formula for z-score is your data value minus the mean divided by the standard deviation. So Sarah's SAT score was 1,380. We'd want to take that minus the mean for the SAT, which was 1,000, and divide that by the standard deviation for the SAT, which was 200. Well, if you plug all that in, if you take 1,380 minus 1,000, that's just 380, divided by 200, it would give you 1.90. So that means Sarah's SAT score was 1.9 standard deviations above the mean. So almost 2. Alicia, let's calculate her z-score. She got a 32 on her ACT. We'd subtract that from the mean for the ACT, which is 21, and divide it by the standard deviation for the ACT, which is 5. If you take 32 minus 21 divided by 5, you would get 2.20, meaning Alicia, she scored 2.2 standard deviations above the mean, which would imply that Alicia scored better, comparatively. Now let's talk about the other part of this lesson that I want to discuss. Let's say I then ask you, what proportion of tests did Alicia score better than? Meaning now I'm asking you for a percentage. Well, we did that with the empirical rule, right? The 68%, 95%, 99.7%. But this does not land perfectly on the first, second, or third standard deviation. We can certainly estimate a little bit, because if this is 2.2 standard deviations, we know that 95% of our data is kept within 2 standard deviations, so we know it's certainly more than 95. But if we want to be more specific than that, we're going to need to be able to find a definitive percentage for 2.2. To do that, we are going to use a z-score chart. Now, for those of you taking this class virtually, this is going to be posted in Canvas. So you'll be able to look in your module on Canvas and be able to pull this up. We want to use this chart to be able to find our percentage. Okay. Now, the way this works, on the left side, on this left column here, you've got all your whole digit, your actual integer digit, and then your tenths place, your first decimal. Your top row has your hundredths place decimals. So if we wanted to find 2.20, we would find 2.2 on the left column, so right here, and then we would find 0 for the hundredths place, which is just that first column right there. So 2.20 would give us a percentage, or a decimal version right now, of 0.4861. Now these are all put in decimal form, so remember to change from a decimal to a percentage, you would multiply by 100, and so that would give us 48.61%. Now that is certainly not our final answer for this. Alicia did not only score in the 48th percentile. Right? She was above the standard deviation. It should be more than that. What's important is that you look at this picture right up here at the top of the chart. This is trying to show you what it's giving you. Any percentage that you get off this z-score chart is only showing you the portion from the mean to your data value. So if we're saying her z-score is 2.20, we're saying on a normal distribution curve that 48.61% is representative of the mean. There's first, second, third standard deviation, so she's about here at 2.2. It's just this distance, just this portion right here that is being shown. Well, if you think about that, Alicia didn't just score better than the tests that were in between here. She also scored better than this entire bottom half. Everyone who scored below the mean, below the average, she also scored better than all of those. In a normal distribution, the mean splits our data perfectly in half. So, if there's an entire left half unaccounted for, that would be 50% of our data. So if we want to know what percent of tests Alicia scored better than, it's not just the 48.61%, it's adding 50 to that, meaning she scored in the 98.61 percentile of ACT test takers in this scenario. The z-score chart is extremely useful, and you will need to use it for this lesson, but understand you are generally going to probably have to either add or subtract 50 to some of the questions, because it's only giving you the percentage from the mean to your data point. It is excluding an entire half of the graph. So if you're not adding 50 to it, 50% to it, make sure that's because you're supposed to be excluding an entire half of the graph. I want to do one more example, talking about how to use the z-score chart and figuring out whether you're adding, subtracting 50, that sort of thing. Let's just, any random number, don't even care about a word problem or anything. Let's just say you found a z-score of 1.64, and I want you to find me the percentage of values, or the percentage of the data, I mean, that would be greater than 1.64. Well, you'd first need to go to your z-score chart. I will go ahead and tell you that if you go to the z-score chart, 1.64 returns you a decimal of 0.4495, which in percentage form would be 44.95%. Okay? You can go double check your z-score chart, make sure you understand where I get that from, but that's what you should be seeing. If you think graphically, visually, about what this is asking you to do, you've got a normal distribution. Here's your mean. 1.64 is somewhere between the first and second standard deviation. So right about there, we'll say. The 44.95% is this portion right here. All of this is the 44.95%. That's not what you're being asked, though. You are being asked to find from the 1.64 greater, meaning to the right. So this is what you've been given the percentage of, and over here is what you're actually looking for. Well, if we know that what we don't want is 44.95% of the data, and we know that the mean is splitting our data in half, then I know that all of this is 50%. Meaning what we need to do is say we have 50% of our data from the mean to the right, and I don't want 44.95% of that. So I would need to take 50 minus 44.95%, giving me a 5.05% as our answer.